Before concluding this section, I want to discuss a few more stuff on pods. And all this discussion will be high level. There won't be any lab as such. Just wanted to make sure that I touch base on the remaining pod concepts. The first thing is the network plugin. You have seen that we have a Kubernetes cluster. There we launch multiple nodes, and inside of multiple nodes we launch multiple pods. But the pods or the nodes are not directly connected to each other. So that is where networking comes into picture, and networking is very central in Kubernetes, and it is really complex to implement. What we have seen in the previous demo is that how containers within the same pod communicate to each other using localhost. We have also seen pod to pod communication within the same node. So that is again very simple. But there's a challenge when one pod wants to communicate to another pod in another node. So natting comes into picture. To avoid that natting, Kubernetes uses something called tunneling. So tunneling is nothing but the communication beyond the node network boundary without natting. And there are a few more things which I have not discussed yet, like services. We'll see how pod to service communications happen in that services section. Now, in the Kubernetes networking model, each of these pods will get its own IP address. So, these three pods in this node, these three pods in this node, and these three pods in the third node, all of them will have their own unique IP address. So, in this particular cluster, we'll be having 9 unique IP address, and the IP address would be taken from the network range which we provide while creating the cluster using dash dash pod network CIDR keyword. As each pod gets its own IP address, it simplifies a lot of stuff in the Kubernetes world because we do not have to explicitly map the container ports to the host ports, which I have already told you. So pods can be treated as similar to individual machines, if you will. And the network model or the network architecture of Kubernetes cannot be implemented by Kubernetes. We need to have some network plugin. And we can use network plugins like Flannel, Calico, AWS VPC when we work on Elastic Kubernetes Service on AWS, and Google Cloud VPC or the compute engine when you work on Google Cloud. We'll see these things when you go into EKS and GKE. So using the network plugin, pods on one node can communicate with all pods on all nodes without NAT, which is very important and very simplified implementation of Kubernetes networking model. One more thing that agents on a node, for example, kubelet, kubeproxy, can communicate with all pods on that particular node. You already know that all of these nodes will have kubeproxy, kubelet, etc. And these processes or programs should be able to communicate to the pods also. That is also implemented by the network plugin only. As a developer or even a Kubernetes administrator, you do not need to go into the details of network plugin, but you should know that the implementation of network plugin is not done by Kubernetes itself. It is implemented by the network plugins. The next thing I want to discuss is the declarative model. It implements something called a desired state. So what we do is we have this Kubernetes cluster wherein we have master node and various worker nodes. Master node has the API server, controller, and scheduler plus HCD. To deploy an application, what we do is we use something called a manifest file. And in the manifest file, we mention the desired state of the application. So far, we have not seen much of the desired state. So far, we have just implemented a pod. If we mention in the manifest file that we need to have at least one pod running all the time and mention it to the master node or the API server of the master node would make sure that no matter what, one pod runs all the time. And the same can be done for multiple pods also. Let's say we are saying that we want to run 4 pods at any given point in time. The master node or the API server will make sure that no matter what, the cluster should have 4 pods running all the time. So we declare the desired state of the application in a manifest file. Till now, you have not seen that in detail. You'll see that when you go into services, deployments, and etc. So once we create the manifest file or declare the desired state in the manifest file, we pass it to the Kubernetes API server using kubectl command. And Kubernetes stores this desired state as application's desired state in HCD database in the master node again. Then it implements the desired state on the cluster. So every now and then, what Kubernetes does, it runs something called a watch loop. So Kubernetes will keep on watching the desired state and it will check the current state also, and it will match those two. If at any point in time the current state does not match the desired state, then the API server or Kubernetes would take necessary actions so that the current state and desired state are always equal. The next thing that I want to discuss is the unit of scaling. You might have already known that the unit of scaling in Kubernetes is always pods, not containers. So what we do is we create containers inside of a pod. You must have noticed that we did not deploy containers by ourselves. We deployed pods, and the containers were created inside of those pods. How those were created? Because we mentioned the container image in the manifest file of pod deployment. Then we created the pod, and the containers were created from the images mentioned in the manifest file. So if you have to scale out or scale in, the unit of that scaling would always be pod. We do not scale by adding more containers, or we do not scale in by removing containers. We add the number of pods only, and that is very important. We have to make sure that you understand that we never modify the containers as such. We do so using pods. Object hierarchy, so far what we have seen is that we have a node which is part of a cluster. The Kubernetes cluster is at the top level of the object hierarchy. Under Kubernetes cluster, you have various nodes, and there can be one or more nodes, but the nodes contain pods. So the lowest level in the object hierarchy is pod. Then we have other layers like deployment. We have other thing behind deployment also, which we'll discuss in our future sections. But I wanted to introduce to the object hierarchy. The diagram should be more like this. We have cluster, under cluster we have nodes, at the lowest level we have pods, and then we have other things in between that we'll see later on. Every Kubernetes cluster need to have an internal DNS service, which is very much vital to the operation of the Kubernetes cluster. So what this DNS service does is, whenever a pod wants to talk to another pod using its IP address, it will go ahead and connect to the Kubernetes DNS. And Kubernetes DNS would know that where to send the traffic to. Meaning that all containers and pods know how to find it. When we'll talk about services, we'll also see that how every new service is automatically registered to the Kubernetes DNS. I'll not go into the details of Kubernetes DNS because before going there, we need to know some other stuff. But I just wanted to touch base on this particular component. Then you have kubeproxy, which sits on each and every node of the cluster, and it is basically responsible for the local networking of the cluster. For example, it makes sure that each node in a Kubernetes cluster gets its own IP address. It also takes care of routing and load balancing of traffic in the pod network, in the entire pod network. Then HCD, which is again very important, as it is vital to the operation of the cluster, it should be highly available. Whenever we deploy a production cluster, we'll see that we'll have HCD in a highly available mode, or we'll have the master node in highly available mode. So HCD is implemented on the master node itself as a file system. How it works is we have HCD database, and whenever we run any kubectl command, let's say kubectl create, once the creation of the object is successful, it keeps a metadata of that object in HCD using key value store. So whenever we run kubectl command, it goes ahead and tallies the HCD database to further its operations. To do so, the API server runs a HCD command behind the scenes. We can get that command from GitHub, but let's say if we are writing kubectl create command and passing it to the API server, the API server will run HCDCTL set command to update the HCD database. We cannot run the HCDCTL command by ourselves until and unless we install it and do the setup, which is most of the times we'll never do. Similarly, whenever we run any, let's say, kubectl get command, it gets the information from HCD using HCD get command, which is a read operation. And this HCD command is executed by the API server behind the scenes. Now, HCD is an open source key value store database which has been embraced by Kubernetes. The final thing I want to tell you about labels and selectors. These are very important because we'll be using labels and selectors a lot in our entire Kubernetes class. So these are our pods. So we have green pod, gray pod, orange, blue pods. So the way we do it is we label each and every pod. So let's say the label of these two pods are green, label of these two pods are color gray. These four, let's say label key is color and label value is orange, so on and so forth. So we mentioned something like this in the metadata portion of our manifest file, that whenever we create a pod, we mention label, and under label we mention key value pair. So here I'm mentioning color and then the value of this key. It can be anything. It can be, let's say, environment, it can be name, it can be location, it can be deployment, etc. Now, once the labels are done, we then use something called selectors to group a particular set of pods. For example, we have seen in node selector that we can select a particular node using its labels. So we can do the same for pods also. There are various types of selectors, by the way. The only thing that we have to mention using the selector or inside of the selector, the label which you want to fetch and be the part of this particular group. So that's what labels and selectors are. So labels are unique labels to pods, and selectors are selecting pods and creating a logical group using the labels which you have put to the pods. So this concludes the pod section. In the next section, we'll talk about deployments.